Hi, everybody, and thank you for taking time out of your busy day to spend with us on this webinar about defibrillator best practices. Joining me today, and you'll hear him speaking, is one of our subject matter experts in the field using defibrillators every day, and Justin Ross out of Pennsylvania. And so, Justin, I'm really looking forward to your input.
Hey, thank you, guys. I'm Justin Ross with Roscoe Solutions. I'm the channel partner for Fluke Biomedical up here in the Northeast, covering Pennsylvania, New York City, and New Jersey. So I'm looking forward to helping you guys out today.
So when we talk about defibrillators, I'm just going to start really with real basics. So some of you have more experience. Bear with us because we also have a lot of people on the in the session here who are just beginning their journey and their career path with testing defibrillators as medical devices. So in defibrillators, we actually have two major types. We have full ACLS, which is advanced cardiac life support defibrillators, and these allow the doctor or paramedic to select the energy levels and be in a little bit more hands-on control of the defibrillator. And then we have AEDs, automatic external defibrillators, and these you will find in all kinds of places, especially at least across the United States and in many parts of the world. You'll find them in libraries and other public buildings, schools. We even have them here at Fluke in our hallways just in case, so that they're handy should someone have a cardiac arrest, because there is a limited amount of time before damage happens to the brain because blood is not flowing during a cardiac arrest. So AEDs are there as a first responder tool. You don't have to know very much to be able to use them because of their design. We'll talk more about that as we get along. Then we also have, especially in the full ACLS defibrillators, we often see pacemakers that are integrated or incorporated into the design of those defibrillators. The purpose for these pacemakers is a temporary external device that can be used to help the heart rate of a patient either be speeded up. So typically, if a patient has a cardiac problem that causes their heartbeat to be slower, we call that bradycardia, then we may want to use a pacemaker in order to speed the heart rate up. There are a lot of reasons for that clinically that we probably won't be able to go into today, but we can go into at a different time. Just want to make it clear that we're not testing implanted devices. So not implanted defibrillators nor implanted pacemakers, because when we do quality assurance testing, periodic testing on these medical devices, we purposely do not want the patient connected. We're going to connect our test instruments instead and do everything that needs to be done to verify the performance and safety of these devices. So just to make that really, really clear. So
for some reason, people just don't like us discharging the defibrillators that are implanted in their chest. I don't know why.
Yeah, that's true. That's true. So when we look at the temporary external transcutaneous is a big word. It just means through the skin. So we're either going to pace through the pads or paddles that we would also defibrillate through, or sometimes there is a separate set of little electrodes that stick onto the patient for the purpose of doing this pacing. The pacer parameters are current that we're going to dial into the pacemaker part of the defibrillator, and a pulse rate. So it will be in pulses per minute, and that will be how we assess how much we're causing the heart to beat, in addition to the much slower natural heart rate of the patient when we need to do this. There's two different ways of pace. There's demand mode, in which case the pacemaker is going to be sensing the patient's normal heart rate. And as I said, remember that heart rate is slower than it needs to be for the patient. And it's going to pace only enough to catch up to a more normal heart rate. So if a normal heart rate is around 60 or 70 and the patient's heart rate is 40 or lower, we're going to use this demand mode pacer so it only paces the amount it needs to make up the difference. There's also an asynchronous mode of pacing where the pacemaker is just going to pace at whatever the rate is that you put on it, independent. It doesn't care what the patient's heart rate is. It's going to pace at whatever it's set to pace at. And that means that the patient's own heart rate may be there plus whatever you put into the pacemaker in terms of what the actual heart rate is.
Just to touch on that a little bit more, on demand pacing, if your heart's beating, if Jerry said that pacer at 60 beats a minute and your heart's beating at 65 beats a minute, there will be no pace pulses. We're not going to be discharging any energy to it. But in an asynchronous situation, if it's set at 60 beats a minute and your heart's still beating at 100 beats a minute, it's still going to be pulsing you 60 beats a minute. So you're going to be catching that shock every time.
Right. And for that reason, there's not a lot of asynchronous pacing that really goes on much anymore. Mostly we're doing demand pacing. And sometimes even in temporary external pacing, sometimes multifocal, which just means that we're pacing more than one chamber of the heart at the same time and in an appropriate way. So if you hear some of these terms when you're talking to the clinicians in your facility, that you'll know a little bit more about what they mean.
Hey Jerry, we just had we had one of our attendees ping in here, and they're asking if there is no beat on a patient, how does a pacemaker detect a patient's naturally paced heartbeat? So I think what they're asking is, how is it going to detect what the patient's heart rate is to judge if it needs to pace or not?
All temporary pacemakers are designed to detect the lack of a heartbeat. And typically you don't pace asystole, which is a flat line, meaning no heart rate. You don't pace them. What you pace is slow heart rates. So there is a heart rate there. So the reason that the pacemaker is designed to not try and pace asystole or flatline is it needs to alarm and call out asystole or flatline because either the patient is dead or we need to do something else besides pacing in order to get the heart to start beating again. These are not just instrument only devices. These are part of a more inclusive therapy or treatment for the patient that includes medications that get delivered in order to help the heart, if it's beating too slow, to be a little bit more excited so that the pacer really helps. Or in that case, that's what we're going to do. So you wouldn't normally pace flatline or asystole. That wouldn't normally happen. Okay, so there are two major types of cardiac life support devices, the pacemaker and the defibrillator, and I think I've already talked to you about when we use each. Okay. So now we're talking about defibrillators and pacemakers, what they do, and I think I've already kind of covered that also. The defibrillator is there to convert ventricular fibrillation, or VFib, back to a more normal rhythm, heart rhythm. It won't always come back to normal sinus rhythm, but it will come back to a more normal rhythm that will help the patient, because ventricular fibrillation, the heart is just sitting there quivering. It's really not beating, it's not contracting, it's not moving blood through the lungs and out to the tissue. So that's why the patient is going to suffer lack of oxygenation all the way out to the tissue and the brain, and that's why we get the brain damage and other detrimental effects all the way to death. So that's what the defibrillator is really there for. It is also there to slow down heart rates that are too fast. So usually get above 120 or 120 or 180 beats per minute. Certainly anything north of that, you're going to need to slow that heart rate down because the patient is at risk of going into ventricular fibrillation with only a little bit of impetus. So typically that is called synchronized cardioversion, and it's also not the first thing that we do. Again, it's part of a series of medications that the patient would receive, like sodium bicarbonate, to settle the heart tissue down a little bit, slow it down, make it so it's not so excitable. And if we can't get the heart rate slowed down sufficiently with that, then we will use synchronized cardioversion, which is a bit more brute force as a treatment in order to slow that heart rate down. So that's also another use of the defibrillator, that is to prevent the patient from going into ventricular fibrillation. Okay, so why is this important and what can go wrong? The important thing is that we find sources of prevent failure of the defibrillator as a life support device before the failure happens in clinical use. So that means we really have to go and test them. There are all kinds of things that can go wrong. Defibrillator batteries may not be fully charged, or there may be some fault in the charging circuitry and therefore not be able to deliver enough energy. Defibrillator charging circuits may have faulty components that prevent the proper assessment of the patient and the proper charging of the defibrillator. So it's important to ensure that we catch those things early, and while they're easy to repair. So there are lots of clinical peer review articles about this, about these adverse events that could happen, and we'll talk a little bit more about those as we go along here. So that's the important thing, is the defibrillator just has to work first time and every time when you need to use it.
On that, we think about where these are located, and we talked about, Jerry mentioned earlier about some of the locations of AEDs and defibrillators. We also need to talk about the fact that these things are carried around in the back of ambulances, stuck in helicopters, in the back of police cars and fire trucks. They're beat up, used. If anyone's ever been on an emergency medical scene, they'll see the stretcher come out of the back of the ambulance with the defib on the top of it. And as soon as they go over the bank and down to the patient, it rolls off the top of the cart and down the hill and into the mud. Even in the hospital, we talk about them. They sit in a hallway on top of a crash cart, and they sit there nice and pretty until they're needed, in which case they're grabbing it and running down the hallway. How often have they forgot to unplug the cord when they took off and headed down the hallway and it's yanked off the top of the cart? So these defibrillators and AEDs have a rough and tough life. Some of them, like when they're in those vehicles, it's cold at night, and this vehicle's outside in the cold, so they're getting frozen at night, and then in the daytime, in the middle of the summer, they're getting cooked sitting in the trunk of that police vehicle. So there's a lot more factors that need to be thought about and the ways that they can be broken, other than just in the normal clinical usage of sitting there on the crash cart in case there's an emergency.
And to Justin's point, when we look at the US FDA adverse events reports, adverse events meaning failures during clinical use, there are more than 72,000 AED, medical device incident reports, since 2005, just in the United States alone. So when we think about around the world how many failures, there's even more than that, at least another 50% more, at least. And so why do we need to do testing on these defibrillators? Well, these are exactly the reasons. Our purpose and our job is to try and prevent these failures during clinical use. And to Justin's point, they are the kind of a device that gets beat up a lot just in the normal use of them and moving to the point where we can get to the patient. It's not all smooth hallways and stuff like it, just inside the hospital. So you can have a look for yourself, not only about defibrillators, but other medical devices right on the US FDA website. It's available for anybody to go and look at and check on. In fact, we went and checked just for 2019, this year in the United States about defibrillators, and there were 3 incidents this year during 2019 in the United States that were reported that we found. 2 of those were AEDs. So it's really, really important that we do our job and do enough testing. The manufacturers of AEDs have, from the very beginning, tried to make them able to test themselves. So there's a lot of internal self-tests that they do, even while they're just sitting there. Nevertheless, you can see 72,000 incidents indicates that we need to do more testing more frequently in order to knock that number down. That's unacceptable, just for your information. Here are some other reasons to test. The US FDA and ministries of health around the world are looking at these same statistics and incident reports. There are international standards for minimum performance and safety of medical devices, including defibrillators and AEDs, where they have to be proven safe and effective for clinical use. And those are written for the manufacturer of the devices, and how that rolls down to the biomedical technician or engineer is through the manufacturer's specifications and the service manual test procedure, and that's brand and model specific. So Zoll has theirs, Stryker now, used to be Physio Control, has theirs, Cardiac Science has theirs, and on and on. So when we're doing testing as biomedical engineers and technicians, we need to be following the manufacturer's service manual procedure in that test, not our own made up one, the one that the manufacturer has created, using the requirements in the standards and adjusting them to match their design of their brand and model of defibrillator. And that's how we get the right testing, where we're all doing the same kind of testing on the device and with the predictable results and results that match up to the manufacturer's specified pass and fail criteria. So who's going to watchdog all of this in hospitals and so forth? Well, accreditation agencies around the world. So who does that include? Joint Commission International outside the United States, DNV, which is also international, and HFAP, which is the Healthcare Facilities Accreditation Program that is going to audit how we are doing the testing on these medical devices and more. So it's important to you. Let me give you one more reason why. In the United States, the CMS, which is the part of the US government that regulates whether and how much the hospital will be reimbursed for cost of care for Medicare patients, and then that rolls down to each of the states in the United States to Medicaid patients, has some requirements also. And they look to these accreditation agencies to verify that the testing has been properly done. And there's where the requirement for following the manufacturer's service manual procedure is a requirement, absolute. You cannot avoid it. You should be doing it. Now, they also have accepted for those hospitals that have databased and have analyzed their failure rates to perhaps modify the frequency of inspection a little bit, but not about defibrillators or anything else that falls under the critical medical device category. Now, that certainly includes life support devices, and it includes life-saving devices like defibrillators and more. So if you think in your hospital that you can adjust down and just do once per year or once every 2 years looking at your defibrillator, guess again. That's not meeting the requirement, And then there's the medical legal side of things, which means if we're not doing what we're supposed to do and a patient is injured or a patient dies, then we're going to court. And even if they settle outside of court on that incident, it will cost the hospital millions of dollars. And where does that money come from? It comes out of your paycheck, or it prevents the ability for you to get one more helper in your biomed department to help you keep up with the testing that you need to do. So this has big implications, not only for patient risk, but also for you in your pocketbook. So here's our first testing poll question. So the question is, how many times a year do you currently test your defibrillators? And we'll just ask that as a general question. And so here's your options: once a year, twice a year, or 3 times or more per year. And do not currently test.
Okay, so I've now closed it. So we have 35% at once a year, 56% at twice a year, 6% at 3 or more times a year, and 2% that don't currently test.
Wow. Okay, 2%ers, that's a problem. And the once, so here's the real deal. It's twice per year is the best answer for this question. Now, to be sure, there are a couple of defibrillator manufacturers that have set their frequency of inspection at once per year. But I'm sure you'll agree, when we looked at that 72,000 incidents since 2005, once per year is not enough. And so typically twice per year is pretty good. And it's about this twice per year is what we would look at for other kinds of life support devices and critical devices in the hospital. So we're sticking with the recommendation of twice per year. So if you answer twice per year, that's great. If you did 3 or more, wonderful. I'm not sure you're actually doing 3 or more per year, but that's okay. You're understanding where we're trying to come from about our recommendation here.
Hey, Jerry.
Yes.
We just had a gentleman ping in here saying that their defibs are tested every day, and I can't help but think, but you're right. You know, in most medical facilities, they do a daily check in all your crash carts and your defibrillators. But are you really going through all the parameters when they do that? Or are they just powering them on, making sure it powers on and the battery's full and the pads are still in service?
Right. So those tests are done for sure, but they're not done by the biomed typically. They're done by nursing, or in the case, Justin, of ambulance services and air medevac, they're done by a flight engineer or someone on a daily routine. But typically those would be done by the clinical staff. The twice per year is what the biomed is going to do. Okay. All right. So there is also, as we look at these automatic external defibrillators, and we look at the newest, say in the last 5 years or so, maybe a little longer, full advanced cardiac life support defibrillators, we see the ability for them to have a little bit of an output energy guarantee. Now, what do I mean by that? That means that for those defibrillators, well, in any defibrillator, the energy level that they are charging up to, whether set by a dial setting by the doctor or the nurse, or whether it's an AED and it automatically already has a setting that it's supposed to deliver. What that setting may be, that value should be what's delivered to the patient at the paddles or the pads. And in order to keep up with the change in the percent of the population that is obese, and oh, by the way, a lot of other conditions, conduction path conditions that can occur, so dry skin, or the patient is real sweaty, or the patient is real hairy, it's got a lot of hair, that normally if they were in an ICU or any other monitoring situation, they would have that chest hair kind of shaved off for where the electrode's going to go. You don't have time for that in an emergency situation where the patient is in cardiac arrest. And Justin, when we talked earlier, you had some examples of that, right?
Well, I'm a 245-pound hairy woolly mammoth myself, so I can pretty much guarantee you the impedance across my chest is going to be much higher than a smaller person who uses moisturizer on a daily basis. And in talking with my wife and some of my medic friends recently, they advised me like, hey, you know how we actually prep somebody in an emergency situation? And I had to stop and think about it. I'm like, oh yeah, you're right. You stick the pad on the person and then you rip it off and bring any hair with it, and then put a new pad on them and we use that one. So we didn't really have the time to skin prep the patient. So yeah.
So it's important because as you can see on the slide, there are lots of different reasons why the patient's resistance to the energy setting is going to be a problem. And so the newer defibrillators have built into them a sensing circuit that's part of the charging circuit of the defibrillator that's measuring the impedance, the transthoracic or across the chest impedance of the patient, sensed through the paddles or these pads that are placed on them. And then it's given it's able to adjust itself slightly within some limits so that what you set is what you get. And that's what I mean by output energy guarantee. But in order to test whether that functionality is working properly, you have to have more than just the standard 50 ohm test load that's required, has been required and built into defibrillator analyzers for many, many, many years. So what do you do about that? Well, we need to have some sort of ability to provide additional resistance values or load values above and below that 50 ohms, because the average obesity of the patients across the world today is really more like 70 ohms, not 50. So we just need to be able to do that. And so you can't test these functionalities with just that one single 50 ohm load. So what do? Well, across the available defibrillator analyzers today, including ours, there are external loads that can be used so that when you're testing the defibrillator, you're able to also test this functionality by keeping the output energy setting at a particular setting and then testing it across more than one of those load values. So you can see that what you end up with is what we call a flat response. So if I have 200 joules of energy dialed into the defibrillator, or that it is set to deliver, that at 50 ohms, it gives me what I expect, 200 joules. But if I have the load at 20, it also gives me 200 joules. If I have the load at 100, it also gives me 200 joules. So you can see that tells us that the defibrillator output energy guarantee is properly functioning. Why? Because a lower load or a bigger load, it still delivers the value that I need it to deliver. You cannot see that if you only have a 50 ohm load. You'll never be able to see and challenge that functionality. So we say there's typically 3 different situations where you need to be able to do this testing. Some manufacturers require that you do this testing as part of their service manual procedure, but you should do this testing as part of your acceptance or incoming inspection test for any new defibrillator that's coming into your building before it goes into clinical use. Trust, but verify. You need to see for yourself that this functionality is working properly. It may have been tested at the factory by the manufacturer you bought it from, but you need to see it for yourself. objective, independent evidence that this functionality is working. How about after repair? So sometimes if you're not doing the repair in-house, it's going out and coming back in. So that's another instance of the acceptance test. But if you just did a repair, even if all you replaced was the battery, you need to retest. And again, I'm not talking about AEDs so much, but I'm really very much talking about full ACLS defibrillators. If you replace the battery or the capacitor or any part of the charging circuit, you need to repeat these tests to ensure that that functionality of the output energy guarantee is really still there, that you didn't interrupt it, that you didn't do something to prevent it from working properly. Okay, so we've already talked about this. I don't need to talk about it a lot more. Oh, the third situation for the testing would be if the doctor or the nurse doesn't feel that the output energy dialed into the defibrillator was fully delivered, they may have a complaint. You're going to go to the clinical unit. You're probably going to have to bring that defibrillator down to the shop to do the testing. And you're going to need to be able to repeat these tests and show, no matter what the load was, that the output energy was delivered. You need to know a little bit more about the incident that occurred that they were complaining about. So what I have done is I have asked the doctor or the nurse, okay, give me a little bit better idea about what I should think the impedance of this patient was. So their body mass. What would you say their body mass was? Big, small, kind of what? And that gives me a sense of where to do my testing. I want to do testing at 50 ohms, but I also want to bracket or test below and above where we think this patient's impedance really was. And then I also want to know how much output energy was dialed in. If it's an AED, it's going to be whatever the AED is set to deliver. And sometimes there are 3 different energy levels and it escalates through. But on the ACLS defibrillators, where the doctor or the nurse is dialing the energy value, we would like to know what was the energy value that you think was not delivered. And we will also bracket that if we can. So we'll test energies above and below and at that value, whatever it was. And the data that the measurements, the data that we collect in our testing will be what we use. We may plot that out as a graph so visually it's easy to understand for the doctor or the nurse. And we'll be able to have a different conversation with them. That conversation will go like this. If I didn't find a failure, then I'm going to show my graph to the doctor or nurse and say, okay, well, I tested this very thoroughly. It shows that it's delivering all its values according to the manufacturer's design. Looks good to me, therefore it must have been something else. We're not doctors or nurses, we can't practice medicine, but we can call out the technical functionality working or not working. If, on the other hand, we did find a failure, then we're going to have the conversation that says, yes, we found the failure, here's what it was, the root cause that we came up with, we did the repair, and we repeated these energy tests and a graph again, and say, and we have returned it back to its full functionality. And that's what these extra load accessories give you the ability to do. It's a completely and much more wonderful conversation with the nurse or the doctor. And you know what it's going to do to their trust in you as a biomed and in your department? It's going to improve it. And I'm going to tell you that I have experience myself, having been the manager of 3 different biomed departments in hospitals in my experience. That's exactly what happens when you're able to have those kinds of conversations with the doctor or the nurse. So you can't just sit down in the biomed shop and wait for them to bring failed devices down to you. You need to engage. You need to make sure you're learning enough about physiology and so forth to be able to have those conversations, and you have the right test tools to be able to help you get that done. All right, so again, best practices. We talked a lot about the output energy testing. One of the things we didn't talk about is a charge time test. That's required in the standard, and most every manufacturer that I've been looking at has has also wanted the charge time test to be done. The charge time test is defined as the 15th, that's 1-5, the 15th maximum energy delivery on battery, not plugged into the wall, on battery. And we run the charge time test on that. If you, for other defibrillator analyzers, you may need a stopwatch in order to run that test. And the test is from the moment you push the charge button on the defibrillator until the ready tone sounds, how long did that take? There's a specification in the standard and in the manufacturer's service manual procedure that tells you what that pass-fail criteria is. And so you need to make the measurement, and that charge time test is part of what we do. We also do the synchronized cardioversion test, and we do a series of output energy tests. For routine testing, like twice a year, normally we would just test with the 50 ohm load. And then, as I said, for acceptance testing or post-repair or this clinical problem, then we do the extra load testing, unless the manufacturer requires those extra loads. But there's more to a defibrillator than just the defibrillator or the pacemaker. The defibrillators today, especially the advanced cardiac life support ones, are including everything that's in a patient monitor today. So that's the ECG, certainly. It's arrhythmia determinations like shock advisory or AED functionality. There's pulse oximetry, or in the case of emergency services and air medevac, we're now seeing a lot more of the pulsed co-oximetry. That's like Masimo Rainbow. So that's SPCO. And you need to have a test instrument capable of being able to do the functional test for that pulsed co-oximeter. You cannot do it with a regular oximeter tester. These devices are actually measuring the amount of oxygen carried by the hemoglobin in the blood. Unlike